Now, comparative properties of alpha, beta, and gamma radiations, that is we are referring to which is more ionizing, which has got more penetration power, what is their time decay, etc. These are some comparison properties of the alpha, beta, and gamma rays. So we have the various properties like nature. So alpha rays, we find that doubly ionized helium atom, that is their charge is 2e, mass is 4 times the mass of proton, the mass is 4 AMU. 4 AMU, that is 4 into 1.6 10 to the power minus 27 kilogram. Now we come towards beta rays. The nature, they are beam of the fast moving electrons. So fundamentally they are electrons, but they are not orbiting around the nucleus. They are originated during the decay of nucleus. So it seems that within the nucleus, there is some variation, like possibly neutrons are decaying and they are giving rise to beta particle. That is the high energy electrons. Then we come towards gamma rays. These are electromagnetic radiations of high frequency, travel in the form of photons, charge 0, rest mass 0, and we find that it is h nu over c square, that is equal to h over lambda c. That is their energy. We come towards other properties regarding velocity, ionizing power, and penetration power. So, in the case of alpha rays, first we come towards alpha rays. Their speed is comparatively lesser as compared to light, and the value varies from 1.4 into 10 to the power 7 to 2.2 into 10 to the power 7. And V alpha velocity is about nearly 0.05 c. So it is not very essential to remember the exact value or the range of the speed, but you can remember that V alpha is normally 0.05 of the velocity of light. Beta rays or beta particles, they travel with 1/10 the speed of light, so speed ranges from 1% to 90% of the velocity of light, that is 0.9 c. For gamma rays, the speed is exactly the same as that of velocity of light, that is 3 into 10 to the power 8 meters per second or 300 million meters per second. Ionizing power, that is maximum for alpha rays. The ionizing power is less for alpha particles and more for, that is, the ionizing power is less for gamma rays but more for alpha particles. And in the gamma rays, this ionizing power is very less, or rather no ionizing power. Now we come towards the third property, that is the penetration power. So alpha rays, penetration power is small and it can only penetrate 0.01 mm thick aluminium sheet. Beta rays, the penetration power is about 100 times that of alpha rays, can penetrate through 1 mm thick aluminium sheet. And in case of gamma rays, the penetration power is maximum, about 30 millimeter thick aluminium sheet. The other properties are about the range, that is in air medium, what is the penetration power, that is what the meaning of the range. Alpha rays, range is very small. Beta rays, the range is more than alpha rays, that is few meters in air. And gamma rays, range is very large, many hundreds of meters in air. Then comes the nature of spectrum. The line spectrum for alpha rays, beta rays, continuous spectrum, and for gamma rays again the line spectrum. Then in case of interaction with matter, alpha rays produce heat, beta rays also produce heat, gamma rays produce photoelectric effect, the Compton effect, and the pair production. Regarding Compton effect, that is, a gamma rays photon can split up due to interaction and will move in the different direction. Regarding pair production, when a photon of gamma rays of energy 1.02 MeV breaks up, it gives rise to a positron and electron. That is pair production. And when electron and positron interact, then it converts to two photons of gamma rays, each with energy 0.51, million electron volt, or a single photon of gamma rays with energy 1.02 million electron volts. So when electrons and positrons interact, the phenomenon is called annihilation. And whenever the photon splits up into electron and positron, the phenomena is known as pair production. So pair production and annihilation are inverse phenomena. In one case, the energy transforms to matter, and in other case, the matter transforms to energy. Well, now we again come towards another property, effect of the electric and magnetic fields. We find that alpha rays, they suffer small deflections by electric and magnetic field. Beta rays suffer large deflection due to electric and magnetic field because they are charged particles, and gamma rays, they have no charge, so they are not deflected by electric and magnetic field. So they pass undeflected in the region of electric and magnetic field. Now the other property is the photographic plate, that is we are referring to fluorescence. So property is effect of photographic plate and zinc sulfide. So it is not necessary that zinc sulfide, we can have barium sulfide also. So alpha rays exhibit fluorescence when it comes in contact with zinc sulfide. Beta rays affects the photographic plate and produces fluorescence. And gamma rays, again they produce fluorescence when they come in contact with zinc sulfide. It must be taken into consideration that what difference is there in fluorescence and phosphorescence. In fluorescence, when the radiation falls on the material, it begins to glow. And when we cut off the radiation, the glow disappears. But in phosphorescence, what we find is that even if we cut off the radiation, the glow continues. That is what the difference in fluorescence and phosphorescence. Now, we are coming towards the mathematical attitude of radioactivity. The general equation of radioactivity is n is equal to n naught e to the power minus lambda t. So, when we speak lambda, we are referring to decay constant. It's the exponential equation. And we will find that as the time on the x-axis is increasing, the decay that will be going on, leaving the less number of atoms. We find that if the number of atoms are n naught at t is equal to 0, then in the first half-life, n naught will become n naught over 2. In the next half-life, it will become n naught over 4. In the third half-life, it will become n naught over 8. So this type of variation is in geometric sequence. Earlier, it was 1, then 1 by 2, then 1 by 4, then 1 by 8, and so on. So whenever the expression is in exponential form, then the variation in the number of atoms will be in geometric sequence. That is, the ratio remains constant. So now we come towards the original concept. Let n naught is the original number of radioactive atoms. Radioactive sample in time t is equal to 0. T is equal to 0 means when atoms have not started decaying. When decay started, let n atoms exist in time t. So n naught atoms will exist in t is equal to 0, and n atoms will exist in time t where n is less than n naught and t is greater than 0. Therefore, n atoms exist in time t. If half-life of the radioactive sample is t, then if small t is equal to capital T, then n is equal to n naught over 2. N naught over 2 atoms exist in time t, capital. So capital T is half-life, and t is that instant of time where n atoms are existing, and if small t and capital T are equal, then in that case n will be equal to n naught over 2. So we have written n over n naught is equal to half. First equation. Now the general equation of radioactivity is n is equal to n naught e to the power minus lambda t. From this equation, we will again get the value of n over n naught, which is found to be e to the power minus lambda t. Then we equate the value of e to the power minus lambda t with half, and we will use the concept of logarithm. So here we have mentioned here n over n naught is e to the power lambda t. and this negative exponent is converted to positive exponent, equation number 3. Then n over n naught is 1 over 2. So 1 over 2 is 1 over e to the power lambda t, and therefore e to the power lambda t is equal to 2. We can further explain it by taking the log. That is log 2 base e is equal to lambda t, or 2.303 log 2 base 10 is equal to lambda t. And from this we can get the value of lambda or t. Now if t is equal to t, then e to the power lambda t is equal to 2. Now we have made the logarithmic calculations and we have found that lambda t, that is t is equal to 0.6931 over lambda. This capital T is called the half-life of the radioactive sample. It is the time in which half of the sample disintegrate. So lambda is different for different radioactive samples. Lambda is given in per second, per minute, per hour. Average life is known as the average life of the radioactive sample. Average life is given by function, that is Ta is equal to 1 over lambda. That is the reciprocal of the decay constant. So if we take Ta over T, that is average life and the half-life ratio, this becomes 1.44. So average life is about 1.44 times of the half-life.